Welcome to partial fractions requiring long division. So the idea here is sometimes we'll have integrands with rational functions. So sometimes we'll have integrands which are rational functions. Which can be simplified with long division. So in particular, this happens when the numerator has degree greater than or equal to the denominator. If that is the case, then we should simplify first. And then run partial fractions. So, for example, if we should wish to evaluate the indefinite integral, which is the integral of 3x cubed plus 17x squared minus 6x minus 16, all in our numerator, all divided by x squared plus 5x minus 6, and then times dx. We have a cubic divided by a quadratic. Right? So we have a cubic over a quadratic. So the first thing we should do is simplify. If we set up our long division, we put that numerator of 3x cubed plus 17x squared minus 6x minus 16 on the inside, and our x squared plus 5x minus 6 on the outside. X squared times 3x would get us up to our 3x cubed. If we do our multiplication, that gives us 3x cubed plus 15x squared minus 18x. If we then subtract that off, we will have 17x squared minus 15x squared leaves us with 2x squared. Negative 6x plus 18x will be plus 12x. And then we bring down that minus 16. X squared, we would have to multiply by 2 to get 2x squared. Then do our multiplication step. We have 2x squared plus 10x minus 12. If we do our subtraction here, we wind up with the 2x squareds cancel out. 12x minus 10x is 2x. Negative 16 plus 12 is negative 4. So we wind up with 3x plus 2. Then we have plus a 2x minus 4, which is still being divided by our x squared plus 5x minus 6. So at this point, we have that our integral of 3x cubed plus 17x squared minus 6x minus 16 all over x squared plus 5x minus 6 dx. This is equal to the integral of 3x plus 2 plus 2x minus 4. That 2x minus 4 is all divided by x squared plus 5x minus 6, and then dx. Of course, this is equivalent to doing the integral of 3x plus 2 dx, and then adding on the integral of 2x minus 4 over x squared plus 5x minus 6 dx. That first integral we know how to do very straightforward. And that first integral, we would be looking at 3/2 x squared plus 2x. Then we have plus the integral of 2x minus 4 over x squared plus 5x minus 6 happens to factor as x plus 6 times x minus 1, then dx. We are going to run partial fractions on that fraction there. So if we run partial fractions, we are looking at 2x minus 4 over x plus 6 times x minus 1 is equal to capital A over x plus 6 plus capital B over x minus 1. If we clear the denominators, we have 2x minus 4 is equal to A times x minus 1 plus B times x plus 6. If we set x equal to 1, that will clear the A term, and we wind up getting then the 2 times 1 minus 4 is equal to A times 0 plus B times 7, or -2 is equal to 7b, giving us that B is equal to -2/7. Similarly, to clear the B term, if we set x equal to -6, then we would have 2 times -6 minus 4 is equal to A times -7 plus B times 0. This gives us -12 minus 4 is -16 is equal to -7a. And so we get that A is equal to 16/7. So we have our 2x minus 4 over x plus 6 times x minus 1 is equal to 16/7 over x plus 6 plus -2/7 over x minus 1. So that gives us that the integral of 2x minus 4 over x plus 6 times x minus 1 dx is equal to 16/7 times the integral of 1 over x plus 6 dx minus 2/7 times the integral of 1 over x minus 1 dx. This, of course, is equal to 16/7 times the natural log of the absolute value of x plus 6 minus 2/7 times the natural log of the absolute value of x minus 1. And then we have our plus c. So putting this all together, we have that the integral of our original 3x cubed plus 17x squared minus 6x minus 16. All over the x squared plus 5x minus 6 dx is equal to our first component was 3/2 x squared plus 2x. And then we have our remaining integral, which was that plus 16/7 times the natural log of the absolute value of x plus 6 minus 2/7 times the natural log of the absolute value of x minus 1, and then plus c. So again, partial fractions and long division followed by partial fractions allowed us to evaluate this more complicated rational integral. And that is it for our main primary integration techniques. In the next videos, we will start looking into what happens when our integrand is not continuous and we wish to take a definite integral, or what happens if our definite integral has bounds at infinity.